Welcome to this eLearn Security video on Android Runtime Analysis Part 2. In this video we are going to see how bad code implementations may lead to vulnerabilities such as SQL injection, directory traversal, and data leakage in general. During the video we will target several applications to explain some of the techniques that can be used to exploit these kinds of vulnerabilities. Let's start inspecting our first target application. We've already installed it on our virtual device and it's called ELS Note Pro. This is a very simple application that allows the user to create, edit, and store notes on the device. Once it starts, we can see a list of notes that we have already created. If we click on the top right button, we have two options, Secure and Add. Add allows the user to create new notes. For example, let's try to add a new note and save it. Let's add a title for the note and set its content. Once we are done, click Confirm to store the note. As we can see, the note has been stored and we can now read and edit it by selecting it. Here we see the note we have just created and we can continue editing it. The other option, Secure, allows the user to access notes protected by a password. To read these notes, we first need to insert the correct passcode, which in our case is ELS. Once we insert the right passcode, some other notes stored on the device are loaded. So the ELS Note Pro application is very simple. Some notes are available by simply running the application, while some others are only available if we insert the right passcode. What we want to do now is to test the application in some way to see if it's vulnerable and might allow other applications to access these notes. Let's suppose that we don't have access to the device, meaning we can't access the application data from a shell, but we can install our malicious app. So we want to create an application that, without declaring any permission, may be able to read the content of the notes stored on the device. Right now, we know that the application stores the notes into a database, and that the database is stored in the application folder, which, as we also already know, is sandboxed. This means that we wouldn't ever be able to directly access the database files of the application. So we have to verify whether the application exposes any provider, receiver of service, that may be useful to access these files. We have already downloaded the application.apk file on our machine and decompiled it using APK tool. Here we have the folder which contains all the decompiled app files. Let's inspect the application's manifest and check if there is something interesting in that file that will help us. As usual, we can find some valuable information in the manifest, such as activities, intent filters, and providers. Here's a defined provider and we can see that there's no permission set to it. This means that we could be able to query the application via this content provider without specifying any permission in the malicious app. The first thing to do now is to get the provider URI to use and then create an app that tries to query the target content provider. We have also decompiled the target application using dex to jar, so let's load the decompiled jar file into JDGUI and inspect the source code in order to find the correct URI to use. Here's the jar file in our app. Let's open it. In the left pane, we can see all the packages of the application. Let's open and inspect the package named com.els.notepro, which should contain all the application classes files. We can see a new package named Content Provider. As you can imagine, this file may contain valuable information about the URI to use. Let's open it and see the source code of the class named Content Provider. If we inspect the code, we can see a lot of information useful to reconstructing the correct URI to use. Here we have the authority value, then the base path. A few lines after, we can see the complete URI used by the provider. As usual, we can see that it is composed by the string content followed by the authority and then the base path. Now that we know this information, let's go into Eclipse and start configuring our attacker application named Note Pro SQLI. We have already created the code to use the query, the content provider, and add the results to the text view object of the app. What we need to edit is the URI that the app is going to use. In the last part of this code, we run the query against the provider, and then we use the returned cursor to access the result set that we are going to append in the text view object. Once again, right now, we just need to provide the correct URI to use. If we go back in the decompiled application, we can simply copy this value from here. So let's copy and paste it in our application. If the query works, we should get the notes stored in the database. So let's run the application and see if it works. Let's wait a few seconds until the application is loaded and installed on the device. As we can see, our malicious app loads and we can see a list of the notes stored in the database. This is exactly the result obtained by running the select query. We can see the values for each column and row of the database. If we inspect the results more closely, we can see that there is no trace of the notes stored as secured. So it seems that the target content provider by default returns only the notes that are not protected by the passcode. Let's then try to tweak our code and check if the selection argument of the query is vulnerable to SQL injection, and then see if we are able to read all the notes. So let's create a new string variable with the following value: _ID equal 1 or 1 equal 1. If the selection parameter is vulnerable to SQL injection, the query should work and should return all the notes stored in the database. Before running this code, we have to pass the selection value to our query, so let's select the third argument and let's change null to selection. Now that the code is complete, let's save it and run it. As we can see, the query works, and we can see all the notes that are stored in the database. There is still a problem. The notes stored as secure are not yet displayed in this view. This may happen because the secure notes are stored into a different database. That's why, even if the selection is vulnerable, we are still not able to read them. What we can try then is to test if the projection parameter is vulnerable as well. So let's delete the selection and create a new string array variable named projection. The projection should contain a list of columns to return. In other words, it contains what follows the select statement of the query. Since we want to test if it is vulnerable to SQL injection and we don't know the name of the database, we can try to inject a query that returns the schema of the application database. To do this, let's edit projection as follows: quote, asterisk from SQLite _ master, semicolon, quote. With this string, the query that is going to be executed will be select asterisk from SQLite _ master. Note that we are missing one important character at the end of the projection string. The semicolon at the end of the string tells the DBMS that the query is finished and can be executed. This instructs the DBMS to execute the query till it reaches the semicolon and then ignore what follows. Now that the query is complete, let's add the projection variable to our query and run the code. As we can see, we get the database schema. This means that the projection parameter is also vulnerable to SQL injection. Also, now we know that there are a few different tables in the target database. We can see a table named Note Pro Secure. Let's then go back to our code and edit in order to get all of the data in that table. Since the projection is vulnerable to SQL injection, we can run almost every query against the database. So let's edit it and change SQLite _ master to Note Pro Secure. This query will return all of the data stored in this table. Let's run the code and see what we get. Here indeed we see the content of the note stored as secured. So using the application content provider and its vulnerable implementation, third-party applications may be able to retrieve all of the data stored in the target application database. In the previous example, we have seen how to use a few SQL injections against the content providers to access restricted data. What we're going to see now is how we can use the content provider misconfigurations to access and read files using the target application context. The target of our test will be the application named File Browser. Let's run it and see how it works. The simple app allows us to browse and read part of the device files and folders. Here, for example, we can see and read the content of the file, simplefile.txt. Note that we can access only the SD card files. If we try to go back into the root folder, the application prints out that we cannot reach the root folder. Now that we have a brief overview of the application, let's inspect its Android manifest and check if it defines any provider. We have already decompiled the application using APK tool. Here we see we have the files of the app and its manifest. As we can see at the bottom of the manifest, the application exports a provider named access file. Since the exported value is set to true, other applications may be able to use this provider. We can try to use this provider and see if we are able to use it now to read files stored on the device. Let's go back into Eclipse and open our new attacker application, which is File Explorer Exploit. In the main activity, we have already wrote a few lines of code that we will use to get and read files. At the beginning, we get the text view object that we will use to display the results of our operations. In the next line of the code, we have to set the URI to use. Right now it is empty, but we will have to edit it in just a few seconds. Here, open input stream is used to open a stream on the content associated with the URI. Then we simply read each line of the input stream content and add it to the text view object in our attacker activity. What we have to edit right now is the URI to use. So let's first set the URI scheme by adding content. Then we have to add the package name of the target application, which we can retrieve from the target application manifest. Now we should append the name of the file we would like to open. If we go back in the target application, we can see that when the application starts, it uses a root folder, the SD card folder. So we can suppose that the application reads files starting from this path. Let's then try to add the path or the file name of a file that is stored in the SD card. Here, for example, we can see that in the SD card root folder, we have a file named simplefile.txt. Let's go back in our attacker application and add this file name to the URI path. If our guess is correct, when we run the app, we should be able to open this file. Let's save the edits and run the application to see what happens. As we can see, the app successfully opens the file and prints its contents. Now that we know we can use the target provider to read files, we can test if it is vulnerable to path traversal. This means that if the target application doesn't validate the URI provided, we could be able to read files that are outside of the SD card folder. This is very similar to the path traversal that we usually see in web applications. In order to test it, we have to add and repeat the characters .. to the URI, then add the path of the file we want to read. Also, to be sure whether the app is vulnerable, we have to read a well-known file outside the application's context. While for web applications hosted on Windows servers, we use files such as boot.ini, in Android, we can use the hosts file stored in the etc folder. So let's tweak our URI and add as many .. characters as we need until we are sure we have reached the device root folder. Then, let's add the path of a well-known file, which in our case will be the etc/host file. With this URI, if the target application is vulnerable to the path traversal, we should be able to read the contents of this file. So now let's run our application and see if it works. As we can see, we are able to read the file, meaning that the application is vulnerable. This also means that we are able to now read any of the files using the application context. In other words, we can read files in the application sandbox as well as every file on which the application has reading privileges for. We just need to change the path /etc/host with the full path of the file that we want to read. For example, let's open a shell on the device and check if there is any file stored in the application folder. Let's navigate the folder and list all the files. Note that all the files stored in the application folder are sandboxed, meaning that we should never be able to access them from other applications. Here, in the Files folder, we can see we have a file named protected_file.txt. This is a good target for our test. Before exploiting the directory traversal to read this file, let's prove that we can't directly access and read this file from our attacker application. To read the file, let's first comment the code used for the directory traversal and then copy the following snippet of code. The simple code tries to access and read the content of the file protected_file.txt and then print its content in the text view of the application. Here we create a new file variable and we pass the path of the file to read. As we can see, it's the same path of the file listed before within the ADB shell. Here we try to read the file content and add this to the text view object of our attacker application. So let's run the code and see if it works. As we can see, we are not able to get the content of the file. The text view is empty. Let's go back at Eclipse and inspect the logcat view to check what happened. We can see a system error message. As we had supposed before, our application failed to open the file because it doesn't have the privileges to read it. Indeed, we get a permission denied. Once again, this happens because the file has been created by the application in its own sandbox. So in other words, the application can't access it. Now that we know that we can't directly read from the other application, let's use the directory traversal to access its content. So let's change the URI and set the path of the file we want to read, which once again is the file stored in the application files folder. Let's paste the path to our URI and let's delete all the useless characters. Let's save the code and run our attacker app. As we had supposed, this time it works. Indeed, here is the content of the file. We can double check this by opening our ADB shell and running the cat command against the file. Here we see the content of the file, which of course is the same as displayed in our malicious app. As we've seen during this video, if an app exposes a content provider and doesn't implement security controls correctly, other applications may be able to exploit it through SQL injection or directory traversal and get private data stored within the vulnerable app. Thanks for joining us.